please.
Thank you very much. So hello, everyone. Good afternoon. Thank you for giving me the opportunity to talk here at this nice event. What I present to you now is something very basic, a lot of formulas, so I apologize for that. But I thought I need to increase the number of formulas this day. And I'm accounting for all the talks before, I can promise. And I'm talking about something very basic, which is called optimization versus sampling. And it's joint work with Alexander Falk here in the audience, Andi Habring also in the audience, and Christoph Griesbacher. In our research, we are very much interested in solving inverse problems, and we're dealing with Bayesian formulations of inverse problems. So the idea is there's a prior distribution of knees, and let's pick out one knee, maybe the knee of Randy, put it on the MRI machine. There's some physics going on. So you know there's a forward operator and noise, and then you have measurements in the k-space. And then, since this is a random process as well, I pick out one sample Y, which is the measurement data, and then I would like to reconstruct Randy's knee correctly. And this we basically do in a Bayesian formulation by means of Bayes' theorem, which tells us that the posterior is proportional to the likelihood, which in case of MRI imaging is very well defined here with a Gaussian distribution involving the forward operator, times the prior. Okay. For me, the Bayesian world is quite nice because for me this is like logic with uncertainty. The complicated thing in imaging is that while the likelihood term is very easy to model based on the physics, the prior is very hard, px, and usually nowadays this is learned from data. Okay, so once we have the posterior, we have the big problem of which point estimate we can pick from the complete posterior distribution. And making use of risk formulations based on a certain loss function, there are two dominating approaches. One is the 0-1 loss approach, which yields the maximum a posteriori estimate. This means selecting that knee that maximizes the posterior distribution, and this gives me in the end a very well-defined optimization problem. So this is optimization. However, maybe this is not the best choice because the map could be a very rare sample. So therefore, we can also think about taking the expectation, the posterior expectation. It's also called the minimum mean squared error. That is that sample that minimizes the weighted quadratic distance weighted by the posterior to all samples. And in order to approximate the MMSE, we need sampling. So how different is sampling from optimization? What do you think? Very different or very similar? It turns out it's not so different. So the most basic algorithm for solving an optimization problem is, I think, gradient descent. Everyone should know gradient descent. So you see here iterations based on the gradient. They make gradient descent steps with a chosen step size tau. What can we do for sampling? A very famous and also popular algorithm, for example, in diffusion probabilistic model, is the unadjusted Langevin algorithm, short ULA. And as you see, it just looks like gradient descent plus noise. The important thing here is that the noise term is scaled properly. However, both the gradient descent and the ULA algorithm are very slow, and therefore the question is, can we find faster algorithms? And this is actually what our research is about. In optimization, many researchers have found very nice algorithms to speed up, for example, gradient descent, Nesterov, heavy ball, and so on. But it seems that the sampling literature is much less developed. So let's consider the most easiest problem between sampling and optimization. This means sampling from a high-dimensional Gaussian, and the optimization point of view is solving a quadratic minimization problem. Sampling means generate IID samples from this high-dimensional Gaussian, and optimization means solving the mode of this Gaussian. This is a bit a boring problem because the mode is mu. Therefore, in optimization, we assume the mode somehow is hidden in this right-hand side term b here, which is q times mu. Because if you know mu, then optimization is trivial. So in few dimensions, both sampling and optimization is easy. Thank you. 3 minutes. I will speed up. But in high dimensions, this can be very complicated. But a very fruitful idea to solve high-dimensional problems is divide and conquer. So it means we need to split up our problems into simpler subproblems. And again, in sampling and in optimization, there are two distinct approaches which are very much related. In sampling, this is skip sampling. This means we split up our problem into two vectors, x1 and x2, just split them up. And now it turns out we only need to provide samples from a lower dimensional Gaussian distribution. And then we have this alternating sampling strategy, and this is exactly two-block Gibbs sampling algorithm. In optimization, you can do exactly the same thing. It's the famous Gauss-Seidel algorithm. I guess everyone familiar with numerical linear algebra has stumbled around the Gauss-Seidel alternating minimization algorithm, and the same idea also works here. For example, when we compare now these red lines here with the mean of the Gibbs sampling algorithm, we see Gauss-Seidel is nothing else than noisy. Gibbs sampling is nothing else than a noisy Gauss-Seidel algorithm, exactly the same algorithm, just with or without noise. So what can we do to speed up? Everyone in numerical linear algebra knows successive over-relaxation. It's an easy method to speed up the Gauss-Seidel algorithm to make solving linear systems faster. So you introduce a relaxation parameter, and if omega is close to 2, then you have speed up. It's a similar idea to extrapolation. This was already proposed in the 50s, and only 30 years after, Adler observed that you can do the same with Gibbs. You have exactly the same algorithm, introduce exactly the same over-relaxation, and it was even proved that you can match the same convergence rate. So now what can we do now? Let's again consider the unadjusted Langevin algorithm here, gradient descent plus noise, and now we make a trick, which we found. We split up the noise term into two equivalent noise terms, so that the variances add up, and we just call the first part y. And then it turns out this is nothing else than an alternating Gibbs sampler. We sample y from a Gaussian with mean that and that noise, and then we sample x from a Gaussian with mean y and that noise. And additionally, we can speed it up using the over-relaxation parameter. Now we have here y and x, and then after doing some work, we have seen, okay, we can reduce it back to an algorithm that only works in x. And then we found an accelerated sampling algorithm, which we termed the inertial Langevin algorithm, short ILA. And looking to the optimization literature, it turns out this is exactly the sampling analog of a well-known algorithm, the heavy ball algorithm, which is known to be an optimal gradient descent algorithm for smooth and strongly convex optimization problems. Just the difference is that we have a particular noise term, and what is very important here, that we properly scale the noise with the relaxation parameter. So here's just a simple graphics that shows that when we compute the MMSE for an inverse problem, the higher the relaxation parameters used, the faster we get convergence. And the reason for that is when you look at the autocorrelation of successive samples, it turns out that the autocorrelation is even sometimes negative, and this improves the effective sample size. And then we know from the approximation that we can get better estimates. That's also the end of my talk. We think there is an ongoing transition from pure optimization algorithms to sampling algorithms, and there are a lot of fruitful ideas in optimization which just need to be brought over to sampling. And this allows us to perform Bayesian inference, for example, for solving inverse problems in imaging, and uncertainty quantification in high-dimensional problems. For details, convergence rate, there will be a preprint very soon out, and also Alexander has a poster here where I see some of the details. Thank you very much. Questions? If there are any.
Yes.
Hi, Tom. May I ask a first question? So I'm a little bit lost with the take-home message.
With the formulas.
Maybe. But could you, in a simple words, without formulas, say, so what is the end benefit of switching to the sampling compared to the optimization?
Sampling means sampling, drawing samples from a distribution. So and samples can be used to compute the posterior expectation, which you cannot do with optimization. And you can also compute posterior variances, and this means you can perform uncertainty quantification. These are the main differences.
Okay, thank you.
So in Langevin sampling, one problem that you have is when you have several modes, right? And the mixing between these modes is typically a problem. So one thing you can do, of course, is to increase the noise initially, like annealing the noise or something.
Yeah.
How does this relate to your method?
It does not relate at all. You can also do annealing here, of course. But the momentum term, which is known from optimization, helps you to overcome small modes, for example. It can, since you have a velocity you keep during sampling, you can jump over these small modes. But for bigger modes, of course, you need some tempering scheme as well, and so on.
One more. We can take one more.
May I ask, so you said that there's this analogy with the heavy ball algorithm, and that you also have there's some theoretical results. So are they identical, or is this part MK? Does it lead to differences?
The theoretical results are quite different because, I mean, in the heavy ball algorithm, convergence is measured, for example, based on function values or how close you are to your global minimum, because this is usually applied to strongly convex optimization. And in sampling, you have a very different distance. Usually, the Wasserstein distance is used to check, the samples you generate that define a distribution. How close is this distribution to the true distribution? And similar as in Lagrange sampling, you cannot sample from the right distribution, so it's a slightly biased distribution, and this depends on your step size gamma here. So it's a slightly smooth distribution from which you can compute samples. But you can easily also make the samples true samples by introducing a metropolis step.
Perfect. Thank you so much. Can we hear it again?
Thank you.